Hello, we're team number 4. This is our mechanical design class on project 1. We are the group number 4 and we're going to talk about intelligent cars. My name is Kamal Alonso, Jose Castro, Andres Adria. The very first idea of intelligent cars was born in 1960s, although the first vehicle really developed was 20 years later. This idea was to automatize the vehicle to go in any condition of weather or terrain. This idea was brought to the table by military of prototype automatic vehicles in mid-1980s. After this happened, the idea of intelligent cars grew up and was transferred to the civil sector government worldwide, launched by the first prototypes. When the first study was successfully complete, the car industry wanted to develop a line of production of real cars. In the mid of 1990, the testing of autonomous vehicle on real roads was one of the most important milestones achieved in the industry of intelligent cars.
The basic sensing and actuation technologies for intelligent vehicles are readily available on the market. The key challenge to integrating new technology is heavily dependent on the control strategies associated with the sensor data processing and reasoning. Sensing the state of the environment surrounding the vehicle is a critical aspect of intelligent vehicles application. The most difficult function for intelligent vehicles is road scene understanding. These include locating key landmarks, the road, other vehicle, pedestrians, traffic signals, road signs, and other obstacles. The figure on the bottom left shows a vehicle sensing the environment. It includes different sensors for light detection, identity of the driver, blind spot sensor, parking sensor, and also a vehicle detection. In order to protect the driver's state, vision sensors must be included. They can monitor a driver's fatigue by observing the direction of the driver's eye behavior. In an emergency, knowing the position of the driver's head can assist in the safe deployment of airbags. Communication technologies enable interesting intelligent vehicles application, allowing vehicles to communicate with each other on the highway in order to improve the safety and efficiency on the road system. Applications include intersection collision avoidance, emergency braking, and sharing of the road and traffic condition information. The most common communication between vehicles that we found are the vehicle to roadside infrastructure and also from vehicle to vehicle. Digital maps are widely used in commercial navigation systems for route guidance. Such system will be improved in real-time updating of the map occur from traffic information. Additional functionalities to be added include curve approach warning, curve speed control, traffic sign information, and speed limit information.
An intelligence vehicle with tracking road system and lane detection have been done since early of 1980s. Based on this, the most important role is played by computer vision, although generally laser cameras can detect the road and lanes. Computer vision also make an important role in roadside detection, due to a road signs used to set of a well-designed shapes, color, patterns, and are located at certain heights and position in the road makes an easy task for computer vision to detect them. The detection is done using a collection of colors and shapes detection schemes. As roadside detection, the color and pattern machine are also a technique used for detection of traffic lights. Although this task is not complex goal to reach, it makes vehicular application difficult. In the vehicle detection, this has been achieved addressing a large variety of sensor technology, ranging from vision to lidars and from radar to sonars. Despite the old vehicles don't have the same shape and color, they are at the same characteristic and feature the same large size and same materials. Once the road lane position is detected, the position of the vehicles is predictable. In the pedestrian detection, the direction is the most difficult task in intelligent cars. The appearance of pedestrians is challenging due to the pedestrian shape can change within a very short time and there are not clear variants in color, texture, or size. And no assumptions can be made about posture, speed, of a visibility part of a human body such as the head. But machine learning methods have applied to this problem with the comparison of stereo vision.
For advanced driver assistance, we found interesting applications such as collision avoidance and mitigation. The goal here is to create automated system. Such system has several advantages over a human driver. They have much quicker reaction times. They have also access to sensors such as individual wheel speed and sleep plus external sensors such as radars. They also have access to individual vehicle controls. If those systems had ideal situation awareness, it could in many cases do a better job of avoiding a collision than a human could. Adaptive cruise control is a logical extension of a standard cruise control to also include keeping a safe distance from the preceding vehicle. If there are not vehicles in front of the car, it follows a set speed as with the standard cruise control. Parking assistant is also a low speed aid. In a typical scenario, the driver initiates the system by pushing a button when driving past an empty parking space. The system measures the length of the space using odometry, measures the position of the car in the front and in the back using short range sensors, and infers the position of the curb by assuming that the surrounding cars are standardized cars parked near the curb. Lane changing assistance is the next extension in partial autonomy. It combines line keeping and adaptive cruise control with blind spot monitoring. If the car can safely overtake a vehicle, then a line change is overtaken and speed is unchanged. Otherwise, the adaptive cruise control slows the vehicle down.
The other useful features cars will have is the driving monitoring. This system will scan the driver's face by observing non-common behavior patterns and will be able to know if the driver is in conditions to drive. This includes fatigue, any impairment, and even if the driver is distracted. To increase safety, advanced airbags will be also implemented. Sometimes regular airbags save lives, but other times it harms people instead because sometimes they are just too close to the person. These advanced airbags will have sensors to detect how is the best way to deploy. Also, when an accident happens, the vehicle will immediately make a call to the authorities to report the accident, making it less the time it takes an ambulance to arrive at the accident place. Automated vehicles will bring many benefits to our society. The most relevant is going to be that the traffic will improve since it's being said that people will no longer own cars. They would just need to request the self-driving car and it will come to pick that person up. All of the vehicles will be guided by magnetic markers which will be on all the roads.
We also make a SolidWorks model of what we consider a car for the future. This car it is designed for two persons and has integrated a radio frequency identification to identify the divisions on the road, a global navigation satellite system. It also has a vehicle kinematic state, inertial navigation to localize the exact position of the vehicles around. It includes a sensor to identify the blind spot and parking assistance. People will get used to intelligent car systems such as sensors and communication from vehicle to vehicle. The only impediment of this technology is the ability of industry to deliver this technology with total safety. An important question will arise when intelligent vehicles make public transportation more desirable. How safe will they be? These questions are the fundamental base for smart vehicles on future transportation. People must decide what's best for society and a rich set of alternatives.